All right. Thank you everyone for joining today. And if you haven't done so yet, I opened the poll. So please answer the poll so we know what our audience looks like. And this is the third webinar organized by Science-Sci. My name is Akane Abasi. I'm a graduate student at Purdue University and also a member of Science-Sci supporting team. Science-Sci is an international web platform to empower research and enrich diversity of biodiversity sciences. And we have been hosting this series of webinars to boost conversation about diversity, equity, and inclusion in biodiversity and forest sciences. And we are developing a white paper out of this webinar series. So I just posted on the chat, but if you're interested in joining, please go to the link in the chat. I believe you can see the chat hopefully now. So if you can leave your name and email address there, you're all welcome to join the white paper. Also, please remember to mute yourself during the talk, but feel free to open your video. We'd love to see your faces. And we will have a Q&A session at the end of the talk. So feel free to post your questions in the chat, or if you prefer to speak, you can also raise your hand during the Q&A session, and you can unmute and ask the question yourself. So let's see how the poll looks like. I guess most of the people have already answered the poll, so I will finish it and share with you all. All right, so we have a big number of audience today, almost 30 people, more than 30 people joining. Thank you for joining. We have audience from all the continents pretty much, majority from Europe, Africa, Asia, North America, Latin America, and 4% from Oceania. That is great. And moving on to the affiliation, we have, I guess, more than half of the people are joining from university and academia, research center, but there are also people from the government, officials, and individuals as well. And your gender, female, male, I guess this is a good distribution, considering that our science is still a little bit male dominated. So yeah, thank you very much for sharing where you're joining from and your affiliation. So first, I'd like to introduce Dr. Jinjin Liang. He is physically in the Purdue meeting room. Dr. Liang is an associate professor at Purdue University and also the founder of Science-Sci and the coordinator of Global Forest Biodiversity Initiative, GFBI, and he will give a brief opening remark before the talk. So Dr. Liang, please take over.
Hello, everyone. Can you hear me? Great. Welcome to Science-Sci. And this is our third webinar series. And sorry for the little bit of technical difficulties in the beginning of today, but it is my great pleasure to welcome every one of you. And so first of all, before we start, I'd like to ask you to please switch on your camera so that we can take a group photo, please. So if everyone can switch on your camera, and Akane and Ankita, could you close the spotlight so that everyone can be on the screen for the first time, for the same time, so we can take a group photo all together. Right. Is there a way to show everyone? Akane, are you able to capture everyone? just go to view and show and select the grid view so that everyone is in the screen.
Okay. I have 2 pages. There are so many people.
Okay, yeah.
I can take pictures.
Yes. Take one screenshot for each one.
All right. Everyone smile then. First one. And the second one. 3, 2, 1. All right. Thank you, everyone.
Hey, thank you very much, everyone. And so before we start, I'd like to remind everyone another thing is because we are writing together this white paper. And so if you would please leave us your name and contact information. And then we will be in contact with you so that we can develop this white paper together. So that's another thing I'd like to remind us. So today it is my great honor to introduce our third guest speaker, Dr. Patty Carroll. So Patty has a bachelor's degree in physics and with a minor in mathematics and chemistry from Siena College. And after that, she had a master's degree and also a PhD degree in astronomy from the University of Washington. So she's now a senior sustainability strategist and applied scientist with Amazon Web Services. Okay, and without further ado, Patty, it is all yours.
Great, thank you for the introduction. It's great to see such a diverse audience from so many different regions around the globe. And to be quite honest, I'm a little bit intimidated by the density of scientists and researchers in the audience. It's been quite a while since I was speaking to a science-focused community. So let me go ahead and share my screen. Oh, it says host disabled participant screen sharing.
Can you try it again? I just changed the setting.
And let's see if we can make presenter view work.
Yep, I see it.
Great. So today I'm going to be telling you a bit about cloud computing and more specifically AWS cloud computing and applications for science broadly and with some case studies in biodiversity and nature-based solutions. I can tell you a little bit more about my background. My degrees are in physics and astronomy. I got my PhD in 2016 from the University of Washington. But during my PhD was about the time that the field of data science was emerging. And I was excited about using technology and using data to make decisions and to uncover new insights. And that's where my passion was. That combined with a draw out of academia actually somewhat coincidentally landed me at the Climate Corporation, which was an agriculture technology company that was dedicated to leveraging data at scale, IoT, sensor data, satellite imagery, weather, climate models to help farmers make more informed decisions. So I was with Climate Corporation for a little over 5 years. And during that time is when I became familiar with agriculture and agroecology. I worked very closely with domain specialist scientists. And my title over that time changed, but the scope of my work was always about leveraging data, applying the science, and generating new insights, and helping climate to develop and test new product features in their digital platform for farmers. And so my work spanned from pest and disease management to carbon sequestration in soils and biodiversity applications, identifying underperforming land areas that could more optimally be used for habitat restoration. So that's a little bit about my credentials. And I joined AWS actually over a year ago, not quite a year and a half, in July of 2021. And at that time, there was a new team dedicated to sustainability solutions for AWS customers, and I was very eager to advance the use of technology and help accelerate the use of technology at scale to drive sustainability solutions. So for my talk today, a high-level agenda, I'll introduce AWS at a high level. I'm not going to go too deep here, but I imagine there's probably some people in the audience that aren't really familiar with the concept of cloud computing or what Amazon Web Services does. I was familiar with AWS. I used AWS while I was a researcher, but never put much thought into why. So I want to introduce cloud concepts at a high level and AWS at a high level, and then talk a bit about sustainability at Amazon and AWS, because that sort of sets the foundation for the work that I do and the remainder of the presentation, where I'll dive into how you can leverage cloud computing on AWS to accelerate the scientific process and the innovation cycle. More specifically around accessing and utilizing big data at scale and facilitating large-scale compute workloads and collaboration across geographies, really globally. And then I'll end the presentation with a series of customer case studies. I'm probably going to end up using some jargon that's industry specific or Amazon specific. Customer is one of those words that we use pretty religiously. It's kind of built into Amazon's culture that we work backwards from the customer, and we always put the customer first. And the customer can be anyone or anything that relies on us or our services. And so customers are AWS users, they can be stakeholders, they can be our customers or clients. And so I just wanted to put that out there when I use customer to give you that context. Okay, so starting it off with high-level cloud concepts. Cloud computing in a nutshell is the on-demand availability of data storage, compute resources, and networking resources. Ideally, you're not thinking about these things too much. You're just able to make use of them. But with the exponential increase of data available from many different sources and different and increasing demands of computational workloads that are being required for the average scientist or the average researcher, the compute infrastructure needed can be a high bar to meet, and the skill sets that you need to leverage it efficiently take up most of your time. And we'll talk through that a little bit more in some of the use cases here. But cloud computing is often used in the context of hyperscale computing. And so hyperscale refers to the ability of any computational system to scale appropriately as the increased demand is added to the system, whether that's data or computation. And hyperscale clouds like AWS have functions that are distributed over multiple locations, and each location is its own data center. So this is an illustration of the different AWS regions, and each region can have multiple data centers and availability zones. A data center is actually like a physical building with a lot of computers, a lot of servers in that building. It's a dedicated space for hosting compute. And so when you're subscribed to AWS and you're using cloud services, you're accessing those computers over the internet. And so AWS has 27 specific regions globally. And as I mentioned, each region has multiple availability zones, and that's attached to a data center, an actual physical location. So the cloud isn't just a imaginary thing. There are actual physical locations and computers associated with what the cloud is and what it provides. So 27 launched regions, 87 availability zones, and we can get into more specifics around actual local zones and smaller scale and direct connect, where you actually have a fiber optic cable like directly connecting for faster speed compute and data transfer. There are over 410 points of presence, and this basically means we're accounting for edge locations, and edge compute is like where you have kind of offshoots of the core AWS availability regions. So I don't want to really get into much more detail on AWS infrastructure. I don't think it's that useful to this audience. But I did want to just introduce the AWS cloud as this global infrastructure of compute that is available for on-demand use. So besides the infrastructure, we also provide solutions and frameworks to help optimize computational workloads. And AWS has published what we call our well-architected framework. And there's traditionally been 5 pillars. As of just about a year ago, we added the 6th pillar of sustainability. But each of these pillars represent our focus areas in developing new services and new capabilities so that our customers, AWS users, don't have to think too hard about security or the reliability or the efficiency or the cost of their infrastructure. We believe that each of these pillars helps reduce the undifferentiated heavy lifting of the IT infrastructure so that our customers can focus on the applications to meet their needs. I'll talk a little bit more about the sustainability pillar in a few slides. Before I jump into an introduction to sustainability at Amazon AWS and how we approach these challenges, I wanted to just check to see if there's any questions. Okay. So I find it useful, and in giving presentations, it's generally well received to introduce what we mean by sustainability coming from Amazon and AWS. A lot of people just think about the e-commerce platform of Amazon, but Amazon actually has many, many different businesses, and AWS is just one of those businesses. And some of this means that we have to talk about the culture at Amazon and our leadership principles. Just before I joined AWS, actually less than a month before I joined, Amazon added a leadership principle. And our leadership principles are kind of guideposts for making decisions and prioritizing action at AWS. And so there's historically, I mean, they do get updated over time, not that frequently, but this and another leadership principle was added just last year to embody the responsibility that we have to our customers, to the planet, to our communities, to help create the new solutions that are needed for a more sustainable future, and our responsibility to be sustainable in the services that we provide. In 2019, Amazon co-founded the Climate Pledge with Global Optimism. And this is our commitment to achieving net zero carbon by 2040. The significance of this is that it's 10 years before the Paris Agreement. And the Climate Pledge is sort of setting our guideposts for sustainability action. There are really just 3 core principles, the first of which is regular reporting and disclosure publicly for our scopes 1 to 3 greenhouse gas emissions, and other sustainability impacts. Like to date, and still the focus of the conversation around sustainability is very heavily on emissions and greenhouse gas emissions, but that narrative is starting to shift to be more holistic around ecosystem health and why, actually like taking a step back and understanding why we're reporting emissions. And maybe that's just a proxy, and understanding the risk associated with it on businesses and the impact to the environment of our businesses. The second principle is carbon elimination, and this is where we focus most of our effort in reducing the emissions and the impact of our businesses. And then the third principle is using credible offsets to neutralize any remaining emissions. And I know that's a hot topic, and we'll talk a little bit more about what that means and how we're approaching it at Amazon. But the gist of it is that credible offsets, they need to be obviously additional, they have to be quantifiable, they have to be real and permanent, and they should also have socially beneficial attributes associated with them. So this is just a quick highlight slide that we like to share on Amazon's sustainability journey. From disclosing our greenhouse gas emissions and publishing reports. Sorry, was there a question? No, okay.
There was actually one question in the chat.
Oh, okay.
From Josh. He says, is auto scale example on ECS just a specific method or for hyperscaling, or are they distinct concepts? Sorry.
Yep. So auto scale is one way to achieve hyperscaling, but hyperscaling can mean a lot of different things. And so we would have different architectures or patterns for leveraging services on AWS to meet a particular hyperscale need. And so if that's a data hyperscale application versus like a modeling focused application, or maybe you need to stream data in real time to many different geographies. Autoscale, for those that aren't familiar, is really about the ability of AWS when you launch some services and you have, and you're in AWS and you have a workload running, and then the demand on that workload increases suddenly, it can automatically scale up and add more server capacity so that your computer doesn't crash. Essentially, your workload doesn't crash. So that's one tool that we provide on AWS to help with hyperscaling. Okay, so the highlights I want to point out here is that Amazon has become the world's largest corporate buyer of renewable energy, which has a huge impact on reducing our emissions from energy usage in our operations. And then Amazon obviously has a large delivery network for distribution of goods purchased on our platform. And so funneling Amazon is funding new solutions by investing through the purchase of electric vehicles and through dedicated programs that are actual venture capital funds to help our customers and partners and third parties to innovate and to drive new solution development. Okay, I think that's all I really wanted to touch on here, but we'll provide these slides. If you have any interest in diving more deeply into any of this, you can find our public sustainability website rather easily. Just Google it. I shouldn't say the word Google, but a little bit more on renewable energy. We currently have over 379 projects around the world to generate renewable energy. And this puts us on a path to achieve 100% renewable energy across all of our operations by 2025. And this is actually a lot faster than originally planned. We were originally targeting 2030 to hit this target, but we're now on a path to achieve that by 2025. This has a lot of significance to AWS sustainability because the bulk of our impact is the energy use of our data centers and of that compute. So I have a few slides to talk a bit about Amazon's work in nature-based solutions and elaborate a little on the third principle of the climate pledge for generating credible offsets. Offsets are just one component of what nature-based solutions can be. But in general, the nature-based solutions program is really science-driven, led by scientists, PhD scientists. The aim is to really follow the evidence and the scientific research in order to funnel funding to initiatives, including research initiatives and innovation projects that are most critical to staving off the most catastrophic effects of climate change. We focus on supporting the systems, the tools, and the development of new scientific knowledge to support scalable business models for nature-based carbon removal. And we focus on large-scale transformations that would not be likely to occur without significant new investment. A few examples of where we've dedicated funding to nature-based solutions include supporting family forests in the US, more specifically the Appalachian Mountain region of the eastern US. This region has been identified as being disproportionately important for conserving biodiversity and mitigating climate change. And Amazon has committed $10 million to help kickstart family forest programs so that family forests, especially on the East Coast and eastern US, most of the forest land is privately owned, whereas in the Western US, there's much more publicly owned land. So this program is dedicated to helping families that own forests to sequester carbon. And this is in collaboration with the Nature Conservancy. Another project is focused on nature-based carbon removal in Brazil. With the Nature Conservancy, again, Amazon launched the Agroforestry and Restoration Accelerator with the goal to restore native rainforests to naturally trap and store carbon and mitigate climate change. This also creates a more sustainable source of income for thousands of local farmers. And then we are also investing in green cities or smart cities through urban greening and urban forestry programs. And this highlights a few different commitments that we've made across Europe, in the UK, in Italy, and in Germany. There's a lot of benefits to urban greening, including especially when it's focused on communities that are otherwise underserved, that often have higher exposure to pollution in various forms, and that lack access to natural spaces. And then from the environmental perspective, increasing urban biodiversity, improving air quality, and improving stormwater management, for example. I'm just reading the question here that came up in the chat. When Amazon works on projects focused on carbon sequestration, either to offset its own operations or as part of the investments, what kind of verification monitoring are you doing? Okay, I can't answer that question in this forum, but I would be happy to follow up with you offline. David, if you'd like to email me your question. It's not that it's proprietary. I just would need to confirm like what I'm actually allowed to say about that. All right, and so this is the last one I want to highlight, and this is actually kind of a big one, the LEAF Coalition, Lowering Emissions by Accelerating Forest Finance. The LEAF Coalition, Amazon was one of the signatories in creating this coalition, along with Unilever, SAP, GSK, and probably several more since it was originally formed. This was supported, the program of the coalition is supported by the Science Based Targets Initiative. And the goal is to really halt deforestation by financing large-scale tropical forest protection projects. Okay, let me pause before moving on to AWS sustainability and cloud computing for sustainability. If there's any other questions, feel free to come off mute if you don't want to put it in the chat. Okay. So at AWS, when we talk about sustainability, we bucket it into migrating to AWS, optimizing workloads on AWS, and transformation, leveraging AWS for achieving your sustainability objectives, whatever they may be. For migration, there's a lot of reasons to leverage the cloud as opposed to on-premises infrastructure for the purpose of achieving more sustainable IT infrastructure. AWS joined the data center industry in Europe for creating the Climate Neutral Data Center Pact. This is an industry commitment to be proactive in leading the transition to a climate neutral economy. Regardless of where you are in the world, migrating to the cloud for the average, compared to the average on-premises owned, like privately owned data center, results in improvements of efficiency, energy efficiency, and thus reducing the carbon footprint by up to 80%. With the path that AWS is on, Amazon is on to achieve 100% renewable energy across our operations, that would translate, again, on average to a 96% improvement in carbon footprint of your data centers. AWS also, sorry, I'm just moving some windows over here so I can see my notes. Our global infrastructure is built on AWS's own hardware, and this includes purpose-built servers, routers, processors, and we have improved the power efficiency and availability over time. The AWS Graviton and Inferentia are the latest generation of AWS designed processors that are built for the cloud, and they provide up to 60% less energy use for the same performance than comparable instances or server types. This is our most power efficient processor, and making this kind of processor available to our users in their decisions around workload, architecture, and execution is one of our ways that we help our users optimize their cloud for sustainability. AWS also has multiple initiatives underway to use water more efficiently and also use less potable water to cool our data centers. We use real-time sensor data to adapt water use to changing weather conditions. Our water use strategies are very location specific and watershed specific, as they necessarily have to be, and they take into account the local water management and availability patterns. AWS is the first data center operator in Northern Virginia that was approved to use reclaimed water with direct evaporative cooling technology. And this basically means that they don't have to use drinking water for cooling the data centers. And it's surprising if you're not familiar with utilities and regulations, it's surprising how difficult it is to be able to achieve this outcome. In another US region, AWS partnered with local utilities to build new infrastructure that enables the reuse of 96% of the wastewater that's discharged from cooling of our data centers. So water and energy are both used for cooling the data centers, and there is a trade-off there. If you use less energy, you often need more water, and vice versa. And so it's important to consider energy use and water use together. A few more highlights on water stewardship. AWS is working with the Swedish municipality of, oh gosh, I'm sorry, I'm not going to be able to pronounce this. And local water supply companies to support an upgrade to the town's stormwater infrastructure. This creates a new wetland just outside of town. And so the new wetland and stormwater infrastructure improvement that's supported by $4 million of contribution from AWS. The project is due to complete in 2026. We also have a project in Ireland that uses direct evaporative cooling systems to cool, which utilize outside air to cool the servers. And this basically means that for 95% of the year, the AWS data center doesn't use any water at all to cool its data centers. Okay, so briefly touching again on optimization. And this is about workloads in IT infrastructure that are already in the cloud. I shared earlier the AWS well-architected for sustainability pillars. The well-architected framework helps cloud architects build secure, really high-performing, resilient infrastructure for a variety of different applications and workloads. I mentioned we traditionally have 5 pillars, and last year we created the sustainability pillar. As I mentioned, sustainability is fairly tied to energy use and also tied to cost optimization, but it was worth it for us to call out sustainability specifically, in part to meet customer demand, and in part to meet our own internal commitments. It's important for our researchers and our developers to also be considering sustainability in the development of our applications as we work with our customers. So the well-architected framework, it's an internal tool as well as it is an external tool to help optimize workloads. The sustainability pillar does add and enhance the framework by providing a way for users to consistently measure their architectures against sustainability best practices for cloud computing, and then identify areas for improvement. So in practice, the building of sustainability into cloud workloads is about understanding the impact of the workload. Sorry, I just realized my mouse is moving around. Understanding impacts, quantifying the impacts, and applying best practices to reduce the impacts. And we provide tips and guidance without going into too much detail, are largely centered around improving the power efficiency, choosing serverless. And this means that if you have a workload or a job, you don't need to spin up an entire server for that job. You can choose a serverless deployment model that only uses the amount of compute that's needed for that job. So you don't have any wasted compute resources. Integrating our instance scheduler so that servers are shut down and terminated when they're not in use, and our cost explorer also helps customers to right size the recommendations of their workloads. And as I mentioned before, auto scaling is another way to help customers right size, because if they do need additional compute resources, you can automatically scale up and then automatically scale down. So lastly, I want to mention the AWS Customer Carbon Footprint tool. And this was also announced a year ago at reInvent. And this is an interface in the AWS console for users to track and measure and even forecast the emissions associated with their AWS usage. So we're calculating the carbon emissions for AWS workloads. You can also understand the historical trends in the carbon footprint, and you can see that alongside the cost optimization, so you can make the best decisions for any given application. And then lastly, we also provide forecasting so that migration opportunities in particular, large migration opportunities, you can see the forecasted trends and emissions as the migration moves forward, and AWS also at the same time is moving toward 100% renewable power. Okay, so the second half of my talk, if I'm not running too slow, will be focused on transformation and use cases of the cloud for science more broadly, and then some case studies in biodiversity and nature-based solutions. But real quick check in to see if there's any questions. Okay. Sorry, was there something? No. Okay. So when we talk about transformation, we often use the term digital innovation, and that is a way to accelerate transformation. And sustainability transformation is really about the innovation of new solutions to accelerate the path toward a sustainable future, whatever that may mean. At AWS, we provide resources to our customers and users to basically leverage Amazon learnings and Amazon processes and mechanisms to innovate quickly with a plan and in a way that allows you to scale fast, fail fast, and iterate. So the first step is identifying customer needs, brainstorming, generating ideas, evaluating the opportunity against whatever KPIs make the most sense, whether that's cost or sustainability metrics, or even user experience and the number of users reached. Innovation is the center of this process, of course, and this is about discovering solutions and doing it in a collaborative way with AWS technical specialists, domain specialists, and with our customers and the Amazon Partner Network. By selecting a solution or a series of solutions, we can then accelerate the development, the actual build, the technical build of a prototype, and then implementation. It's the last stage here, but really this is a circular process where you then deploy the solution into production, capture whatever KPI metrics you need to evaluate that and feed that back in. I wanted to highlight this because this is really the first step in many of the case studies that I'll describe in a bit. From idea to implementation, AWS and Amazon more broadly is stepping up to meet customer needs to help define and plan and design really new solutions. So this is a silly schematic that shows like the typical workflow, and it can go back and forth and around in circles, but a bulk of it is spent in discovery and very little time in validation, and then launch and continuous improvement is just a straight line here, where things move very fast and there's a lot of technical debt that can be accumulated. I'll come back around to this question at the end, if that's okay. And so we have innovation programs with dedicated facilitators to help our customers and our users walk through this process in an efficient way. We use a design thinking approach. We call it working backwards. It's very similar to design thinking concepts, if you're familiar with that, but working backwards from the problem to shape solutions and execute, and then develop the mechanisms for continuous improvement. And we also provide specialists, both, I'm using sustainability very broadly here because it encompasses a lot of different topical areas for different industries, but sustainability is often a horizontal need across industries and sectors. So we have technical domain specialists working closely with cloud architects and engineers to shape solutions. And by solutions here, I mean reusable patterns, the architecture, the blueprint for a common use case of a solution that can then be customized and tuned to a particular need. And so the the innovation cycle that we provide also helps our customers to shape the solutions that we provide at scale more broadly, globally, as well as future services. And it is a two-way street. So sustainable agriculture is a core use case for our customers. And this is often challenging because farmers themselves are typically not AWS users. And so we approach the agriculture industry and our customers that are within the bubble of the agriculture industry, whether they're providing crop inputs, seed, fertilizer, maybe they're providing digital tools to farmers, maybe they're providing financing or insurance. How do we provide them with the tools to accelerate a sustainable future? At its simplest, sustainable agriculture is about how we cultivate the earth to meet humans' most basic needs, food, clothing, and shelter. Emphasis here on food, because most of the cropland globally is used for food production, but we also need to protect our future generations' ability to meet those needs. Biodiversity and nature-based solutions are often used in the context of conversations around sustainable or regenerative agriculture, which is why I want to highlight this. But we know sustainable agriculture is a multifaceted problem, and the conversation historically has been focused on topics like carbon credits or biodiversity. I'm putting that in air quotes because I don't have it on the slide. That doesn't really take account of the underlying challenges and ultimately the goals. So we're working to shape solutions that will better address true farmer needs and less focused. And we do have teams that are focused on the agriculture industry needs as well, but creating space to help those customers that are directly addressing farmer needs without regard to profit. Is there a question? Okay, that's the same question. So just to iterate again, sustainable agriculture, it faces many challenges. We don't have much more land without clearing forests. We can't clear forests without adding more carbon into the atmosphere. We need to use less water, less fertilizer, which is a huge source of emissions, and less energy in producing our food. We need to reduce the footprint of agriculture. Food production itself accounts for over a quarter of global greenhouse gas emissions, and a majority of that is in the actual crop production, and also a huge part of that is animal agriculture. Agriculture is also very exposed to environmental conditions, and so we have less predictable weather patterns looking into the future of climate change. And we need to reduce the risk to people and communities and the planet from our food production systems. And so to help address these needs, we start with data. And I'm going to break this up into data and compute and modeling. And so starting with data, the challenges that researchers and policy makers are facing globally boil down to some common trends in data, and that's, the volume of data is growing exponentially. It's coming from a variety of new sources and also old sources that need to be then digitized and standardized. It can be raw data, it can be derived data, and then you have issues with reproducibility and versioning. Many different data types, different data qualities that's not always quantified, increasingly diverse user needs of the data, and many different applications that are processing and analyzing the data at scale. So we aim to help customers effectively capture, find, access, and utilize the data they need to build new solutions. And a core part of that is the Amazon Sustainability Data Initiative. which is an investment program dedicated to increasing the accessibility of sustainability data on AWS. So there's many different data layers that are kind of highlighted here. This isn't meant to be exhaustive. It's actually a little bit tuned to agriculture and land use sustainability use cases. But several of the customers that we have supported in making data available for free publicly on the cloud are illustrated on the bottom here. If you'd like to explore data sets, you can just go to registry.opendata.aws. This includes ASDI data sets as well as broader open data sets. And the power of this is it's available for free. It's hosted on in a storage bucket in S3. Anybody can access it. It's public. It's also optimized for cloud computing. And this is most relevant for geospatial data sets. You want to have the data formatted in a way that makes it easy to get only the data you need in an efficient manner without pulling down very large, cumbersome data sets and extracting pieces out of all these data sets at the same time. So we make the data available for free in a format that makes it easy to use. And often you can, schedule a job that uses the data without ever having to download it to your local servers or to your instances. So from data, we can talk about actually utilizing data in the cloud in a more effective way to accelerate sustainability action. And when designing a solution, we typically have 4 phases in the process: ingest, transform, learn, and act. I'll briefly explore or share some architectural diagrams and concepts, but I didn't want to go too heavy with architectures. I certainly wasn't familiar with architecture diagrams until I joined AWS, but these are pretty high level flowcharts. S3 is, most people who know anything about AWS are familiar with S3. It's probably that along with EC2 are the most foundational services that we have. It's really a storage service for data storage. So ingest data can come from many different sources. I mentioned ASDI and open data. That's third-party data that's out there and available and you want to use it. So maybe that comes in from AWS Open Data and Amazon or AWS Data Exchange, which is a subscription service that you can access all this data via API. And maybe some of it's coming from IoT data at the edge. And so we have IoT services to optimize the use of sensor data and formatting that and storing it on S3. And then maybe have some other on-premises data, whether that's your own model outputs, for example, that you have stored locally. Maybe it's more metadata that you need to parameterize modeling. And so we want to be able to optimize the storage of this data and getting it all into one place. Transformation is, in this context, more about the processing, whether you are streaming data and making that available, whether you're doing big data processing, a lot of scientific research leveraging climate and weather and environmental data layers falls under the bucket of big data processing, whether you're making that data available for querying for other users via API or through a user interface. Transformation is the second bucket. And learning. This is simply put like machine learning and AI, but can include any type of modeling, really, statistical modeling, anything where you need to infer an outcome or a scientific result. And so we provide a series of services kind of highlighted on the top here for different types of use cases, whether it's natural language processing or image processing or forecasting. And our users can leverage these services to, again, reduce the undifferentiated heavy lifting of machine learning applications and cross-validation. And then the fourth bucket is action, making any solution able to trigger an action. And so AWS Lambda is highlighted down on the bottom right here, and that is a serverless service that allows you to send a command as long as it can be computationally triggered, or maybe there is a user interface where an alert is given or a SMS text is sent. But most often we're talking about like control systems. HVAC is a great example where maybe you want to send a command to the system to change or to stop or to start. This action can also include visualization and services to provide dashboards and applications for actual people to take action. And then, of course, exposing APIs. So action, of course, perturbs the system, so the cycle always repeats. But architecting in these kind of buckets allows you to continuously improve and make better decisions. All right, I'm going to talk a bit about some customer case studies, but let me pause. I think there was one question in the chat, but I've lost my chat window.
I can read a question.
Okay.
From Salvadurai. If I understood correct, you indicated higher efficiency cells for higher water use. I thought higher efficiency, for example, efficient processors would generate less heat and in turn should use less water for cooling. I am wondering if you could clarify this. Thanks.
I think I missed the first part of that question. Could you repeat it?
If I understood correct, you indicated higher efficiency cells for higher water use. I thought higher efficiency, for example, efficient processors would generate less heat and in turn should use less water for cooling. I'm wondering if you could clarify this.
So I think I had said that energy and water kind of go hand in hand rather than efficiency, but maybe I'm misunderstanding the question, or I don't recall when the question came in. But energy is used, most of the energy used in data centers is for cooling. And if you want to reduce energy but still maintain cooling, there's a trade-off with using water for cooling. And so I think the question was talking about using more efficient hardware. And yes, that will reduce the need for cooling. So that's, I think, a little bit, that's another approach to reducing the overall energy demand by using more efficient hardware. But in terms of the cooling itself, you either need to use air or energy that uses air or water-based cooling methods. I hope that answered the question, but feel free to follow up in the chat. Were there any other questions?
No, that's it.
Okay.
We have a question from Purdue.
Sure.
Hello, do you hear me?
Yeah.
Yes, I am Stan from Purdue. I have a question about the advantage of using AWS service for cloud computing. So as a research scientist at Purdue, I use high performance computing resources at Purdue, and it's quite useful. I mean, it's kind of affordable and kind of easy to use. But most of the researchers in agriculture outside of computer engineering would use standalone machines or at most high throughput computer resources. I wonder if using AWS has some advantages with kind of computing efficiency or amount of data storage, or kind of how easy to share data with other researchers or people outside academia, what are the usual codes to do the use the AWS services?
Okay, I think I caught most of your question. And I think that this case study will actually address it a little bit. A lot of researchers still use on-premises HPC compute clusters, and they're purpose-built. And we don't want to and don't need to replicate all of them. There are ways to spin up a cluster in the cloud and to provision it and to make it available, reliable, and usable for scientists. But that's a little bit deeper than I'm able to share on that. I think that between on-premises infrastructure, whether that's for research compute clusters or other corporate use cases, the cloud can be very supplementary. There's a term that we use called hybrid cloud, and we have services and features that are dedicated to optimizing hybrid cloud. For individual researchers, if we were to connect the cluster where the data is stored or the models are stored and make that data available via API, then a researcher can obviously pull that data into their computer. You could also do that entirely in the cloud. If you upload data to the cloud, then a researcher doesn't really need a heavy-duty machine that can handle that amount of data or compute, and they can leverage cloud resources to do that. And they just need an internet connection. Essentially, you could use a Chromebook. And so there's power in using the cloud for that kind of application, because then the individual scientists, they don't need much more than an internet connection to be able to access the data, to run the compute. And you don't even need to use the same machine from time to time, as long as you have, the login credentials to the account. Does that help answer your question?
Yeah, that's a general pros of using cloud computing. It would be really nice if you could compare the codes or kind of process the speed when using standalone machine or AWS. But if there's no a number on your side, it's okay.
I'm sorry, I didn't really catch everything you just said there.
Okay, so you mentioned most about the general pros of using AWS or cloud computing for a researcher. But it would be really nice if there is kind of a cost or monthly subscription pay to use the Amazon Web Service for research uses at the end of the discussion or sometime later.
Mm-hmm. Yeah, let's follow up so I can make sure that I understand your question.
Cool.
If you want to, I don't know if you can throw it in the chat just so that I can read it. I caught most of what you said, but I wasn't entirely clear on some of the words that might have been defining in the question that you were asking. But let me share this case study. Maybe this will help. I think that you're asking maybe a more specific question that we can elaborate on at the end of the talk, or we can follow up on after. Sure, yeah. So this is actually just part of a customer case study, and we'll be sharing this at AWS re:Invent. It's our biggest annual conference of sorts, and that's happening at the end of this month. So I can't share all the details yet and the name of the customer and some of the specifics. But if you're interested, the presentation will be public and it'll be on YouTube probably by mid-December. So feel free to check it out then. But I can share at a high level the customer. This is a customer that collects, creates, and processes like petabytes of data every day, environmental data more specifically. And this data and the model results and the insights is leveraged by researchers and organizations and policymakers across the globe. So they were looking for a managed service to reduce the cost, the time and like the actual resources, energy and people resources associated with sourcing data, managing the data, processing it, and sharing it and making it available to other resources. So the heart of the challenge was to address the fact that scientists today spend a disproportionate amount of time on data munging and data management. And this has been true for a while, but that burden is increasing as the amount and complexity of data is increasing. And they were also, seeking a solution to help improve traceability of the data processing workflow in order to accelerate the validation process for peer review and reproducibility. So this part of a scientist's job is critical. And if you don't have that validation, that traceability and reproducibility, you're prone to errors, to inaccurate data, or incorrect interpretations. And so the goal here was to reduce the undifferentiated heavy lifting on the scientists to automate that process for the data sourcing and management and compute, so that scientists can recover more of their time to focus specifically on scientific discovery. So this is the last architecture diagram I'm going to show. This is an illustration kind of going from this scattered model where you have scientists in multiple locations, and in different locations, they have different access to different data sets and are maybe limited in what they can do by the data they can see and they can import quickly, to a model that really orchestrates the data access and compute across AWS regions, geographic regions globally. So each region would have its own virtual private cloud. That's what VPC stands for. And these would all be connected with IT cloud infrastructure that makes it efficient for scientists, no matter where they are, to view, to discover data sets in a user interface, and then access that data regardless of what region. They don't have to worry about where the data is located, where they have to pull it from, because it's all centralized in this one platform system. So this improves the speed and ease of data discovery and loading. It automates the distributed compute for large-scale modeling and analytics. And it also automates the efficient orchestration of the computational workloads across AWS regions. This is a solution that's really valuable to global collaborations. So a fun Jupyter notebook here for illustration. A little bit, I'm sorry, this is a little bit repetitive. Other outcomes besides the science user experience is the reduced compute time and the compute energy, both for this customer and considering the compute resources that are used by all of the different users of the data set. And so there's actually very significant savings estimated over traditional approaches to data access, and with reduced compute time and a more efficient architecture, significantly reduced energy that goes into that compute as well. I'm sorry I don't have numbers here, but again, feel free to check out this session. It's titled Utilizing Sustainability Data at Scale. And so that's happening at the end of November. And there'll be a YouTube video released shortly after that if you'd like to know more about this specific customer and use case. So I think I want to make sure to save some time. So I'm going to move kind of quickly through some highlights on how AWS users are leveraging the cloud for more biodiversity specific applications. NatureServe is a leading source for biodiversity data in the Western Hemisphere and has been for decades. They work with a network of 100 biodiversity information centers and over 1,000 conservation scientists. Some of you may be familiar with NatureServe already. So what NatureServe wanted was to help address the need for precise species distribution data. And they developed this online geospatial tool on AWS it's called the NatureServe's Environmental Review Tool. You can check it out on their website. I think they have a nice story map. And this can be customized for any given jurisdiction's regulatory environment to help inform land managers and land use decisions from the very earliest stages of planning to the end of the project's life cycle. So this tool helps guide more proactive conservation decisions. Dendra Systems is a technology service provider that is working to address restoration of natural ecosystems globally. The unprecedented level of data in ecology and environmental systems opens up the possibility of really harnessing artificial intelligence to help with efficiently inventorying the ecosystems and identifying problems quickly so that action can be taken. These problems can encompass a lot of different things, but plant condition stress, invasive species like weeds, species decline, and erosion are common uses here. SENIGA is the National Center for Geo-Environmental Information in Costa Rica. This is a technical intelligence unit, and they're using mapping and modeling tools on AWS to integrate, standardize, and help communicate Costa Rica's and share out Costa Rica's environmental data. And then lastly, the Natural History Museum. This is actually, there's not much to share here, but we pretty recently announced a partnership with Amazon Web Services and the Natural History Museum to develop a digital twin for UK biodiversity, building the data platform to store, enrich, and service urban biodiversity data. Each of these I can provide links for. I kind of went through these really fast, but you can read more detail about each of these case studies, including more specifically how they leverage AWS on our website. And I can share those links out after the presentation. But with that, why don't I call it good on the talking and open it up for more questions and discussion.
Thank you very much, Dr. Carol. That was a very impressive number of projects AWS is conducting with cutting-edge technology. And so, yeah, we're going to move on to the Q&A session. So if you have questions, you're free to raise your hand and unmute and speak your questions yourself, or you can also post your questions in the chat.
Sorry, I've lost my screen here. I've got this chat on my other screen. I hope that wasn't blocking your view of the slides.
No, it wasn't.
Okay.
And in the meantime, we have one question in the chat from Javier.
You want to read it?
I know you can go ahead.
Transparency and data public dissemination must be inclusive, almost by definition. The AWS Sustainability Program taking proactive roles to reach those less likely AWS customers that happen to be the ones protecting large. Short answer, yes. The AWS Sustainability Data Initiatives specifically is investment. It's providing free consultation, free cloud credits for high impact opportunities. And the definition of high impact kind of goes back to the guidance around the climate pledge and really what qualifies as credible and impactful. That doesn't take into account the social aspects and would this have happened otherwise or not, and directing our resources to generate the most benefit in the long run. So for AWS services, and I think your question was about AWS sustainability more broadly, and I just answered more specifically around the data initiative. A broader AWS organization actually has a team dedicated to social impact more specifically. And that overlaps with the more, I hesitate to say commercial, but the more industrialized side of sustainability. And so the Sustainability Data Initiative, actually, I mentioned the Registry of Open Data. That Registry of Open Data is itself a separate program, and it's not specific to environmental sustainability, but they help incentivize data access and compute resources, and run a variety of different social impact initiatives that are specifically targeting underserved communities. I can look up some information more specifically to Indigenous communities as well. I just don't have that off the top of my head.
Thank you. I think there is a question from the Purdue room.
Hi, Patty, thank you so much for your presentation. So I'm very glad to know what Amazon has done to conserve the nature and also protect the earth. And so on behalf of Science Eye, I'd like to see that we are very interested in what Amazon has been doing, and I think we have a lot to contribute as well. So when we talk about the data, so Science Eye, in collaboration with our sister initiative, GFBI, which is Global Forest Biodiversity Initiative, we have compiled and collected one of the first and the largest forest inventory database across the world, and that's a ground source data. And we are talking about, we are having hundreds of our members of Science Eye and the GFBI. We lead local crew members. And so to go to the forest, measure every single tree, and then compile them into a global database. And that cost decades of time and also billions of dollars to conduct all those data. And all those data are critical for us to analyze and assess the global forest resources. So in this past year, in this particular year, we published our first estimate of the number of tree species across the world, as well as we mapped the distribution of tree species locally across the world as well in the most high definition map as well. So with that being said, many of the underrepresented groups from the global south regions, we are facing difficulties in getting those data measured now, especially after the COVID and after the deficiency in funding. And so we as Science Eye, we were wondering if Amazon would be interested in, for example, to support the global forest data collection and forest and the local forest inventory as well.
Yeah, that sounds like a pretty ideal use case for the Sustainability Data Initiative and our impact computing team as well, which dedicates more build resources. I'd love to follow up on that more specifically. If you'd like to send me an email, we can have a conversation. I can pull in the right people from the AWS and Amazon teams to talk about what that could look like.
Yes, sounds good.
Are there any other questions?
Yeah, I actually have a question.
Sure.
I wanted to know what it takes to get an account on Amazon Web Services, and what computing resources as an individual researcher I can get if I have an account.
Mm-hmm. Yeah, I think you can just sign up for an account. You do need to enter billing information, but there's a surprising amount that you can do on what we call the free tier. There's a certain amount of compute that's available to you for free. And so you can use that to explore AWS services, to prototype solutions, and things like that. There's a ton of resources available, including tutorials and a GitHub repository with different examples. But I'm pretty sure you can just go to, it's probably not aws.com, is it? It redirects, aws.amazon.com. And in the upper right, you'll see create an AWS account.
Okay.
And it's pretty straightforward from there. It'll walk you right through it. And then I'm pretty sure that it will also direct you to various resources for getting started. There's also, I mentioned reInvent before, but reInvent at this conference, we do a lot of workshops, and they're live in person workshops, but some of them are recorded and also posted on YouTube a week or two after the event. And so that can be another good resource for you for sustainable architecture and some use cases around leveraging climate model data and weather data that's already hosted on ASDI for different use cases, like identifying deforestation or predicting air quality and things like that.
Okay, thank you very much.
Sure.
I have a question.
Sure.
Oh yeah, I'm Stan from Purdue. Yeah, as a research scientist again, most of the individual researchers would do ingest, transform, and learn by themselves. But I think the case in the Amazon will be a little difficult. People might make a team to do the ingest separately and make a separate team for transform and learn as well. So if I wonder, I'm just asking, I'm just wondering about your personal experience when you, I wonder, you could compare your experience when you're doing research in university, when you're doing PhD, and your experience doing some of the work regarding ingest, transform, learn at Amazon.
I'm having a little bit of trouble hearing the room. I caught, a lot of what you said, but I didn't think I got the core of your question around, you're asking about my experience, but more specifically, could you repeat yourself or maybe put it in the chat if you have that ability?
Can you clearly hear my voice right now?
Yeah. Mm-hmm.
Yeah, I am wondering if you can compare your experience doing your research while you're in PhD and doing your research in Amazon Web Service, if you have done some.
Sure. Yeah, my research experience, I haven't done much research in the year or so I've been in AWS, but in my prior role at the ag tech company, I did a lot of research there. And so I can definitely compare. When I was a PhD researcher, we weren't using cloud computing. We had a local cluster for distributed compute. And I was limited to whatever my local computer could handle, like my actual workspace. And then anything additional was a kind of a steep learning curve to understand the basics of parallel computing and optimization with pretty limited tooling and guidance available internally to help with that. And so some of the biggest challenges that I think came to appreciate more later, because that was around the time that data science was becoming a thing and reproducibility as a challenge and issue in science research was becoming a headline. Everybody kind of doing it for themselves. You don't really have one, you have a lot of redundancy. And two, you don't have the transparency and the visibility for validation and verification to make sure that as a scientist, you're not kind of messing up the actual engineering and processing components, because you probably learned to code just to get what you needed to get done, and you didn't actually learn to code properly. And so there's a transition that occurred, and I think it reflects the broader transition in the science and data science community, where more of the ETL jobs were handed off to specialized teams. And those teams, if they were good, they were providing the tools and the guidance for scientists to use that. In my experience, in a science team within research and development, we had a data engineering team, but then there needed to be a specialized team of data engineers, and there needed to be a specialized team of scientists to make sure that scientists were actually getting what they needed to get. And then the engineering team often, maybe if they like misinterpreted or they, decide that there's some trade-offs in the quality or the speed of the data available, it was a point of friction. And so cloud computing, and it's not unique to cloud computing, it just makes it a lot easier because you have these building blocks of services and it's sort of plug and play, and you can package it up or containerize it and hand it to another person where they can just run and reproduce exactly what you have. Or you version your model results and that's stored and it's attached with metadata that allows you to track back exactly how you got to this derived data set. This is like leaps and bounds beyond what I experienced as a PhD student. And it might have been that my bubble was too small at that point. I'm sure that there were teams and especially large scale computing teams, both in the public and the private sector that were addressing some of these challenges. But I think it's much more accessible now once you have the enablement on how to leverage it. Even while I was at Climate Corporation, the scientists were leveraging a platform service that even obscured the actual behind the scenes of choosing the compute resources and optimizing the infrastructure for you so that we could, just spin up a Jupyter notebook and have a nice user interface that automatically has like version control built in and a peer review process built in. That's called Domino. Some of you might be familiar with it. There's other platforms like that. Databricks is one. And I'm sure there's several others. And even some of those platforms, and maybe all of them, also obscure whether you're using AWS or another cloud service provider for the most part. And so we're moving in this direction of creating more of these tools and platforms so that, scientists ideally can really just like focus on the work that matters most for scientific discovery and insights and driving innovation. But there are still some hurdles to overcome. Anytime you simplify a system or you create a derived data set, there's like built-in assumptions that can be problematic later. So it's really about, in my mind, enabling the transparency and the reproducibility and the traceability so that you can see how you got where you are. That was a long-winded answer.
Thank you so much for the your explanation, your experience. Thanks so much.
There's a question here in the chat about scientists are not software engineers and our code tends to be rough and messy. What would the process look like to migrate an analysis from running some process locally? Yep. Lift and shift, anything that runs locally, you can run in the cloud. It's not going to magically make your code better. But we do actually, I know that there are services that are designed for like automating like code review and making smart suggestions. And I know there's some services built on AWS and then there's tools and plugins more broadly that you can leverage. But yes, I can definitely relate to that. I actually postponed my dissertation. So because I knew at that point I wanted to move into industry to do a Google Summer of Code internship. That was pretty much a boot camp in software engineering for industry and for production. And so I think some of that is also, providing the right training to scientists in their undergraduate and graduate careers so that they don't develop that sort of a technical debt of sorts and have to go like relearn how to properly develop code. Yeah, that's my 2 cents on that.
Thank you, Dr. Carroll. I think it's about the time, so it's a good time to wrap up. So I'd like to take a moment again to remind you of the white paper we're developing. Let me post in the chat briefly. Yes, so yeah, please leave your name and email again if you're interested in joining the white paper, and I will hand it to Dr. Lee Young at Purdue to give a closing remark.
Thank you, Connie. And it is our great pleasure to host this wonderful webinar today. And so we ScienceEye, we are here to enrich diversity of the biodiversity sciences as well as forest sciences by empowering everyone, especially the underrepresented groups, to do great research. And to this end, the cloud computing as well as the associated data infrastructure is a key component to the success of this collaboration. And we are very glad to start a conversation with Patty Carroll and also the Amazon Web Services about building up a collaboration between ScienceEye and maybe the AWS and for future research projects. And to this end, we will be working together towards this white paper on just thinking about how we can strengthen the research of the underrepresented communities by building a strong collaboration between the industry partners like AWS and academia. So to this end, we would welcome your inputs and your continuous support of ScienceEye as well as our data compilation process. And so finally, I would like to thank Patty Carroll again for this wonderful talk. And so with that, we will be closing today's webinar, and I'll be looking forward to continue working with all of you on the white paper. Thank you very much.
Thank you, everyone.